Swayam Prabha. Digital India. Educated India.
Hello, welcome to Introduction to Composites. Today is the fourth day of the ongoing week. Today we will do one more example which will help you understand the importance of minimum volume fraction and critical volume fraction, and also how they are actually calculated from data related to different metrics and fiber materials. So, the example is related to fiber matrix system, and what we are going to do is we are going to first see how the matrix behaves. So, this graph is about matrix stress strain response. This is about stress strain response of a matrix. So, how do you then generate this curve? You take a piece of material which is only matrix and you apply some force. This is pure matrix, and you keep on measuring strain and stress in the system and you make a curve out of it. So, on the x axis we plot a strain, and on the y axis we are plotting stress in the matrix material. And this matrix material behaves something like this. Okay. So, this region, so initially it is perfectly plastic, perfectly elastic. So, this matrix material has stress strain response has two curves. OA is perfectly elastic, it is perfectly elastic material. Okay. So, if I leave the strain at a point within the region OA, it will get back to its original position, which is 0 position, and then after A it becomes perfectly plastic. What does that mean? That if I apply a strain which is more than the strain level at A, then it never gets back to its original configuration, it holds that configuration. So, this breaking point in the curve is 2% strain. So, if the strain in the matrix is less than 2% and you release that strain, matrix goes back to its original undeformed position. If you deform the matrix beyond 2%, maybe 3%, then it does not change its shape once the strain and external stress is released, it just stays there. Okay. So, that is there. So, and the corresponding stress level in the matrix is 35 MPa. Now, I am using this matrix and a fiber to make a composite. So, these are the properties of the matrix as given in the graph. For fiber, what do we have? Volume fraction of the fiber is 50%, volume fraction okay, and Young's modulus of the fiber is 70 GPa, and breaking stress of the fiber, strength of the fiber is 2.8 GPa. So, the question is find A. What is the stress in the composite? Stress in composite at 1% and 4% strain. What is the stress in the composite at 1% and 4% strain? B, what are the values for V min and V crit? This is what we have to find. So, we have the properties of fiber, we have properties of matrix, we have the volume fraction of fiber, and with this data which is provided, we have to compute the stress in the composite when I pull it by 1% and stress in composite when I pull it further, so that the strain in composite is 4%, and we also have to find V min and V crit. Okay. So, let us find this. Okay. First we find epsilon F u. So, this is the solution, because to find V min and V crit we have to find what is the breaking strain in the fiber, and corresponding to that breaking strain what is the stress in the matrix, we have to find that. So, to do that, first we have to compute breaking strain of the fiber. So, the fiber breaks at, so this is equal to sigma Fu divided by Ef, and this is equal to 2.8 by 70, that is equal to 4%. So, the fiber breaks at 4% strain. Okay. Fiber breaks at 4%. Another thing we have to compute is Em, Young's modulus of the matrix. So, Young's modulus of the matrix in elastic range, let us find in elastic range. So, this is equal to, so how do we find the Young's modulus? This is OA is the elastic range, at point A 35%, 35 MPa stress, strain is 2%. So, this is equal to 35 into 10 to the power of 6 by 2 into 10 to the power of minus 2. So, that comes out as 1.75 GPa, and above that it becomes plastic. So, the reason I am saying that is, so this is 1.75 GPa. What does that mean? The slope of this line 0 OA is 1.75, right. Slope of OA is 1.75, and if I also had to plot fiber data, then slope of that line would be how much? 70, because this is 70, right. The slope of OA reflects the Young's modulus of the material, and that is 1.75. So, if I have to put fiber data on this, so this is matrix, and if I also want to plot fiber data on this, it will be a very steep line, it will be very steep line. So, let us call this fiber, and this fiber is going to break at how much strain? 4% strain. We have computed that, right. At 4% strain, this fiber is going to break. So, this is epsilon Fu, and when the fiber breaks at 4%, what is the stress in the matrix? 35 MPa. So, this is, say, this point is also sigma m epsilon Fu. Understood? So, this is very important to understand, because we had to figure out what is sigma f at the breaking strain of the fiber. So, now we have figured these things out. So, the next steps are not all that complicated. So, we will find sigma c at 1% and 4% strains. Okay. So, first we will do it at 1%, at 1%. Now, look at this curve again. At 1%, this is 1%. At 1%, the matrix will not break, nor will the fiber, nothing is going to break. So, at 1%, sigma C is equal to sigma F Vf plus sigma M Vm, and this is equal to Ef epsilon F Vf plus Em Vm epsilon M, and we know that epsilon F is equal to epsilon M is equal to epsilon C is equal to 1%. Okay. And we also know EF is how much? EF is 70 GPa. EM we are still in the linear range, right. So, EM is how much? 1.75. Vf is equal to Vm is equal to 0.5, 50%. So, we put all this information and what we get is we compute it to be 358.25 megapascals at 1% strain. Okay. Now, let us look at 4% strain. So, sigma C, see this relation sigma C is equal to, as long as things are not breaking, this relation does not change. Okay. So, sigma C is equal to sigma F Vf plus sigma M Vm. This relation does not change, as long nothing has broken, we can always use this relation when we are pulling composite in the longitudinal direction, we can always use it. Okay. This thing we cannot use sigma M is equal to Em Vm unless the material is perfectly linear. This thing can only be used for linear materials. Now, in 4%, when the strain is 4%, fiber is still behaving linearly, but the matrix is not linear. Okay. But at 4%, what is the stress in matrix? 35 MPa. From this graph we know. So, this value is 35 MPa at 4%, and sigma F is how much? EF Vf epsilon F. Okay. So, this is equal to 70 GPa into volume fraction 0.5 into strain 0.04 plus stress in matrix 35 into 10 to the power of minus 3, because we are putting everything in GPa, into volume fraction 0.5. So, this is equal to 1.4175 GPa. So, even though matrix has become flat, it is helping load fiber take more and more load. So, now we have answered these two questions. First part we have done. Next we have to find Vmin and Vcrit, and that is actually pretty straightforward. Vmin and Vcrit. Now, let us write down the relations. So, what is Vmin? Vmin is equal to sigma mu minus sigma m evaluated at breaking strain of fiber divided by sigma Fu plus sigma Mu minus sigma M breaking strain of fiber, and V crit is equal to sigma Mu minus sigma M breaking strain evaluated breaking strain of fiber divided by sigma Mu minus sigma M this is sigma Fu. Okay. Now, if you look at what is sigma Mu from a graph, at what stress does sigma Mu fail? It fails at 35 MPa. Second question, what is the value of stress in the composite at breaking strain of fiber? The fiber breaks at how much strain? Fiber breaks at 4% strain. We have calculated it. At 4% strain, what is the stress in fiber in the matrix? It is 35 MPa. So, the numerator, so this is 35, this is 35, numerator of V critical and V minimum is both 0. So, if that is the case, then V min is equal to V crit is equal to 0%. So, in this special case, the minimum volume fraction and the critical volume fraction just comes out to be 0. So, even if you put any volume amount of fiber, that will ensure that the strength of the composite is going to be more than the strength of the matrix, and also the failure of the composite will be governed by the case B situation. So, that is the thing. So, this concludes our discussion for today. Tomorrow, we will move on to next topic. So far, we have been only discussing failure of a unidirectional composite in the when it is loaded in the longitudinal direction. Tomorrow, we will see what happens when it is loaded in the transverse direction. So, that concludes our discussion, and we will once again meet tomorrow. Thank you.